In this module, we shall introduce regression for the case where we have models with constant coefficient of variation. As you know, the assumption of constant variance is an important assumption of the standard Gauss-Markov setup. To be sure, we do have variants of the model where we have weighted regression, or for example where we have heteroscedasticity. However, the remedies for these situations largely revolve around transforming the outcomes to a case where we have homoscedastic data, in the sense of having constant variance. In this module, we shall look at a different concept of constant variability, not measured by the variance, but measured by the coefficient of variation. You will recall that the coefficient of variation is a more natural means of measuring the dispersion in data when different outcomes are measured on different scales. One example of this could in fact be to heteroscedastic data. So say for example, we are measuring information on consumption, expenditure and income. This is a classic assumption of the case where we have heteroscedastic data. It is not natural here to assume that all individuals will have the same variability in consumption expenditure. However, it might be reasonable to assume that once standardized by the mean, the coefficient of variation for these individuals will be constant. In this module, we shall look at regression techniques for the case where we have constant coefficient of variation. Learning objectives for this module. We shall first introduce the concept of a constant coefficient of variation. We shall be interested to develop regression models for this situation, and first we will consider a variant of the linear regression model, but this will lead us to the gamma distribution. So we shall first introduce the gamma distribution and next the concept of gamma regression models. Finally, we shall see how to fit these regression models using R. Note that although it is standard to measure the variability of a data set using the standard deviation or the variance, in some cases a more natural measure is the coefficient of variation. So the coefficient of variation is defined by the variance to the power half, that is the standard deviation, divided by the mean. Our requirement is a constant coefficient of variation, and this is given by variance of y to the power half by expectation y is equal to some constant sigma. The implication of this is that the variance function is of the form variance of yi equal to sigma square into mu I square, where mu I is the expected value of yi. So, assuming a constant coefficient of variation leads to a quadratic variance function. Let us first see how we can use a variance stabilizing transformation to ensure that variance of yi equal to sigma square mu I square will hold. The answer is that the transformation which stabilizes the variance to variance of yi equal to sigma square mu y square is log yi. To see this, let us assume a second order Taylor expansion of zi equal to log yi. This is given by log of yi equal to log mu I plus 1 over mu I yi minus mu I minus 1 over 2 sigma I square yi minus mu I squared, assuming that sigma square is small. Taking expectation, we see that expectation of Zi is approximately log mu I minus half sigma square. According to a first order Taylor expansion, expectation of Zi is approximately log of mu I, which means that it is possible to show that expectation of Zi squared is approximately log mu I whole squared plus sigma squared. Using these two relationships, we see that variance of Zi is approximately sigma square. For small sigma square, we have expectation of Zi approximately log mu I minus sigma square by 2 and variance of Zi approximately sigma square. Let us see how we can accommodate this within a GLM framework. So, we need a distribution for which expectation of yi equal to mu I and variance of yi equal to sigma square mu I square. Using this variance function, we can see that it is necessary to use the gamma distribution. The gamma distribution is defined as y follows gamma with parameters nu and lambda, where the density of y is given by f of y equal to lambda by gamma nu into lambda y to the power nu minus 1 e to the power minus lambda y for y greater than equal to 0. To motivate gamma regression, note that for the gamma distribution, it is possible to show that expectation of y is equal to nu by lambda equal to mu and variance of y is equal to nu by lambda square, which we can parameterize as nu over lambda whole squared into 1 over mu. The link function is g of mu I equal to log of mu I. Properties of the gamma distribution, the mean parameterization. Note that for the gamma distribution, f of y is given by lambda of gamma nu into lambda y to the power nu minus 1 e to the power lambda y, which can be written as 1 over gamma nu into nu by mu y to the power nu minus 1 e to the power minus nu by mu into y. This can be reparameterized as 1 over gamma nu y to the power by mu to the power nu e to the power minus nu by mu to the power y into 1 over y. So, this is denoted as gamma, mu and nu, and is the gamma distribution reparameterized in terms of the mean. The skewness is measured by expectation y minus mu cubed by sigma cubed, which for the gamma distribution turns out to be 2 nu to the power minus half and tends to 0 as nu tends to infinity. Two well-known special cases of the gamma distribution. The first is the exponential distribution, which arises for the case when nu is equal to 1. The normal distribution is also a limiting case of the gamma distribution in the case when nu tends to infinity. Gamma regression can be written in terms of a GLM. So, note that the likelihood using the mean reparameterized form is given by L of mu nu y equal to nu minus 1 log y minus nu by mu y plus nu log mu minus nu log mu minus log of gamma nu. This can be brought into the standard generalized linear model framework by rewriting this as nu into minus y by mu minus log mu plus some function c of y and mu. This means that the canonical parameter is given by theta equal to minus 1 over mu, b theta equal to log mu equal to log of minus 1 over theta or minus log of minus theta. The scale parameter is given by mu. Or rather, if we define phi as the dispersion parameter, then phi is equal to 1 over mu. The function b theta is given by b theta equal to log of mu equal to log of minus 1 over theta or log of minus log of minus theta, which means that the expectation is given by the first derivative, which turns out to be minus 1 over theta. The variance function is given by b double dash theta equal to 1 over theta squared or mu squared as required. We can define the form of the residual deviance for the gamma distribution, and this is given by d of y mu hat is minus 2 summation I 1 to n ln of yi by mu I hat minus yi minus mu I hat by mu y. The deviance can be used to measure goodness of fit, and this can be done by using the fact that the deviance is distributed as phi times a chi-square random variable with n minus p degrees of freedom. Note that the canonical link for the gamma distribution is eta I equal to theta I, which is equal to minus 1 over mu. As we know that the mean of a gamma distribution is positive, this implies that eta is negative, and this has more implications for the values of the regression coefficients beta. The canonical link is thus not used very commonly for gamma regression, and the more popular link is the log link. Estimation of the scale parameter. Now, estimation of the regression coefficients can be carried out using the usual maximum likelihood and the IRLS equations. To estimate the scale parameter, we can use the Pearsonian residuals and estimate phi hat as phi hat equal to 1 over n minus p summation I 1 to n yi by mu I hat minus 1 squared equal to 1 over n minus p summation I 1 to n yi minus mu I hat by mu I hat squared. Pearson's chi-square statistic for gamma regression is given by chi-square p equal to summation I 1 to n yi minus mu I hat by mu I hat whole squared, which means that the dispersion parameter is estimated from phi hat equal to chi-square p divided by n minus p. Connection between gamma regression and linear regression. We wish to relate gamma regression with a log link to a linear model on the log scale. Let us consider the log transformed responses and assume that the scale parameter is relatively small. In this case, we have variance of log yi approximately sigma square, and therefore we can use log of yi equal to xi prime alpha plus ei with the assumption that ei follows normal 0 sigma square. So, this is the linear model on the log scale, and as you know, covariance of alpha hat is given by sigma square x prime x whole inverse. For gamma regression, with yi following gamma, mu I and 1 over sigma square, with mu I equal to exponential xi prime beta, we have beta hat follows normal with mean beta and variance I inverse beta hat, where I of beta hat is the Fisher information matrix. Note that for this case, minus of expectation del square L beta, del beta S del beta j turns out to be equal to 1 over sigma square summation 1 to n xis xij independent of beta, and thus I beta hat is of the form 1 over sigma square x prime x. In this case also, covariance of beta hat is approximately sigma square x prime x inverse, and this is equal to the covariance of alpha hat from the log linear model. This means that the distinction between the two models is difficult, and if further that if x corresponds to an orthogonal design, that is x prime x inverse is equal to I, we have that the components of alpha hat as well as those of beta hat are asymptotically independent. Sometimes it is necessary to consider weighted gamma regression. So, we shall explain this in context of the Canadian auto claims insurance data. Let us suppose that yi is the total claim size arising from ni claims in group I with covariates xi. Yi is actually summation j equal to 1 to ni yij, where yij is the jth claim in group I. yi star equal to yi over ni is the average claim size in group I. Now, if yij's follow gamma, mu I, mu independently, we know that this means expectation of yi star is equal to mu I, and variance of yi star is mu I squared by ni into mu. Since yi star follows gamma, mu I and scale factor ni into mu using the additivity property of the gamma distribution, which can easily be shown by looking at the corresponding moment generating function, it is possible to show this result. Thus, we need to introduce weights for a gamma regression for yi stars. Since expectation of yi stars is equal to mu I, the EDA and the diagnostics for the regression, however, are similar to that of the unweighted case. The Canadian automobile insurance claims data for 1957 to 58 can be downloaded from the Oz DASL library. It has been studied by Bailey and Simon Leroy. The data gives the Canadian automobile insurance experience and includes all insurance companies operating in Canada. The variables included in the data set are merit, which measures the number of years since the last claim on the policy; class, a collation of age, sex, use, and marital status; insured and premium. Insured is the earned car years, premium is earned premium in thousands; claims, the number of claims, as well as the cost, which is the total cost of the claims in $1,000. The R code given here shows how to fit a gamma regression of cost by claims in terms of merit plus class. Note that claims is used as a weight. We can look at the results using the usual summary command and the goodness of fit by looking, for example, at the Pearsonian residuals. We can also get an estimate of the scale parameter from the Pearsonian residuals. Finally, we can choose different links, and here we have used both the log link as well as the inverse link function. Regression models, although have the main purpose of modeling the mean of an outcome in terms of covariates, also carry associated assumptions about the variance. For example, the standard multivariate regression model assumes that the variances are constant, that is, we have homoscedastic data. The Poisson model, as you know, assumes non-constant variances and variances which are equal to the mean. In this module, we have considered an alternative situation in which case variability of the outcome is not measured in terms of the variance or standard deviation, but in terms of the coefficient of variation. We have seen how to tackle this using a variant of the linear regression model and also introduced the gamma distribution and gamma regression model as a better alternative for addressing this situation. Finally, we have seen an application to the Canadian auto insurance claims data.